Hello and welcome. In today's lesson, we'll talk about limits, continuities, and discontinuities. This lesson has been prepared for students who are taking the Grade 12 Calculus and Vectors course, MCV4U. We are on Unit 1, Limits, Lesson 3. So let's get started. Continuity of a function is a term we've mentioned in the Advanced Functions course, and we've said that a function is considered to be continuous throughout its domain if we could draw the graph of a function without having to lift the pencil. In calculus, we are going to redefine the meaning of it and enrich it with more specific calculus terms. So we're going to say that a function is continuous at every value x equals a if three conditions are satisfied. Number one, the function must be defined at x equals a. So what that means is if you substitute the value of x, so the specific value of x that you're inspecting, into the equation of the function, you should be able to get a real number. Number two, the limit at x equals a must exist. And in order to find the limit, you must check both left and right-hand limits. And they must be equal to each other for the limit to exist. And condition number three is that the value of the function must equal the value of the limit at the function at x equals a. So in this case, we are going to say that the function is continuous at that specific point. If any of these three conditions are not satisfied, the function is discontinuous. Now, let's take a look at some examples. So the first example is the function y equals x squared, and we're trying to find the limit as x approaches 2 and discuss the continuity at x equals 2. So, as you all know, the graph of y equals x squared is that of a parabola. Okay, and we know this function is continuous, but we're going to use this to illustrate how we can algebraically determine whether a function is continuous or not at a point. So, condition number one, so we must check for condition one. We have to evaluate the function at x equals 2. At 2, the function will have a value of 2 squared or 4. Condition number 2, we must find the limit as x approaches 2 from the right and the limit as x approaches 2 from the left, and that will help us determine the limit at x equals 2. So when x approaches 2 from the right, then the limit would be 2 plus squared, so that would equal 4. When we approach 2 from the left, so 2 minus squared, the answer will be about 4. So we see that left and right-hand limits are equal, which tells us that the limit as x approaches 2 of x squared would be 4. Last condition, we need to compare the value of the function with the value of the limit. So f of 2 equals 4. The limit at 2 equals 4 as well. So the two are equal to each other. Therefore, we're going to say that the function is continuous. So the limit at the given point is 4. The function at the given point has a value of 4. The value of the limit and the function are equal. And that tells us that the function is continuous. Moving on to an example of discontinuity, and we have several examples. There are different types of discontinuities that we observe in functions. The first type of discontinuity we're looking at is the removable discontinuity. Now, removable discontinuity looks like this. So we see a hole in the graph. Now, why do we call this discontinuity removable? The reason why we call it removable is because these discontinuities are caused by the removal of a restriction in a function, or in other words, the removal of an asymptote. So as an example, I'm going to bring in here the equation of a function f of x equals x minus 2 over x squared minus 4. So technically, this function must have two vertical asymptotes because there are two restrictions in the denominator. But because these two restrictions simplify, one of the restrictions simplify, then one of the asymptotes is removed. But removing the asymptote doesn't mean that the function becomes defined at the point. It just means that the function will have a hole at that point. Okay? So the removal of an asymptote at a point will cause a hole on the graph of the function at that point. So point discontinuity is kind of the same or similar to removable discontinuity. So we call this a point discontinuity because the value of the function at the point does exist. So if x equals a, we have f of a as a respective value for y. The limit of the function also exists, okay? But the value of the function and the value of the limit are not equal to each other, okay? So we are going to say that if in the first example, which is a removable discontinuity, f of a doesn't exist, the limit at a exists, right? We're going to say that the function has a removable discontinuity. So in the next equation, f of a exists, the limit as x approaches a for f of x also exists, but they are different in values. So the limit as x approaches a for f of x is different than f of a. And that's the reason why we have a point discontinuity here. The next type of discontinuity is what we call the jump discontinuity. So this is what it graphically looks like. And you can tell why we call this a jump. So the reason why this is called a jump is because if you were drawing this graph, you have to jump by a certain interval, or you have to jump a set of numbers in here to continue drawing the graph of a function. Now, in a case like this, we're going to say that if you approach x equals a from the left and the right hand, you will see that the limits are different. So the limit as x approaches a from the left would be equal to L. The limit as you approach x equals a from the right, it would be equal to R. So the left and the right hand limits are different in value. They exist, but they're different in value. And that causes the function to experience a jump in the y values. Okay, so f of x is jumping. Now, the third type of discontinuity we look at is what we call the infinite discontinuity. Now, remember that the word discontinuity means a break, okay? So here we have a break by 1 point only, okay? And here we have a break by 1 point, so these are kind of similar. Here we have a break by a jump in the x values, so that's why it's called a jump discontinuity. Now, infinite discontinuity is also a break, but the size of this break is not a defined interval like in the jump discontinuity, but it's infinite in length because the jump here would be, or will have the size of infinity. Now, as you can see here in this example, the limit as x approaches a from the left end is negative infinity because the values of y are approaching negative infinity. Now, when you approach a from the right, the value of y is r. Okay? So that creates an infinity length break between the two pieces. So the limit as x approaches a from the right is equal to r, right? The function is defined at a point. It may or may not. We still call this an infinite discontinuity. Now, another type of infinite discontinuity is when the graph experiences something like this. This is what we call a cusp, actually. A cusp is like sort of a vertex where we see that the graph is going all the way up here. So when you approach x from the left and the right end of it, now both are going towards infinity, okay? So there is an infinite discontinuity in here as well. Now, we're going to take a look at some other functions, and we're going to try to determine the type of discontinuity algebraically. We have g of x equals x squared minus 9 over x minus 3. We are asked to draw the graph of this function. So I will factor the numerator and the denominator. And over x minus 3. As you can see in here, we can simplify one of the factors, which means that we are removing an asymptote. So the function gx simplifies to become x plus 3. That will give us the equation of a line, all right, with a positive slope of 1. And the graph of this function will look like this. Okay, so this is a 3 and a negative 3 right here. Now remember that if we didn't simplify, we would have said, oopsie, that we would have had an asymptote at x equals 3. So I'm going to walk along the x-axis and point at x equals 3. Now at x equals 3, the graph would have had an asymptote, but because the asymptote was removed, or the restriction was removed, then the graph will have a hole at x equals 3. I'm going to make the graph a bit longer, and we're going to take a break right at 3, so right here somewhere. Oopsie, that was too big. So I'll make this perfect, don't worry. Okay, almost perfect. So arrows, the graph continues. Now, what we are going to do is find the limit at x equals 3. Now you can tell that as we approach 3 from the left or 3 from the right, the function will have or will approach the value of, let's take a look in here, looks like a 6. So we're going to say the limit as x approaches 3 from the left will be 3 from the left plus 3, which is 6. As the function approaches, or x approaches 3 from the right, the function will be 3 plus 3, that's 6 again. So left and right hand limits are equal, so which means that the limit exists. So we're going to say that the limit at the given point exists and equals 6. The function at the given point is not defined. All right? The value of the limit and the value of the functions are not comparable because 1 doesn't exist. Therefore, the function is said to be discontinuous. At x equals 3. All right, so we're going to take a look at another example, and this is an example of a jump discontinuity. So we have k of x equals x squared. That's the first piece of the graph. And f of x equals, k of x equals 3 for x less than 1. So if we were to draw the graph of this function, then we would have at 1. That's where the functions separate from each other. And up to x equals 1, we would have had a parabola. And for x less than 1, I actually meant bigger than 1 here. The value of the function is 3. So at 1, the value of the function is 3. So we're going this way. So obviously you can tell that there is, there is a jump in the y values here. So we see a jump discontinuity, so we're going to take a look at it from the algebraic point of view. So we're going to say that the limit as x approaches 1 from the left, that's where the x values to the left of 1 are in this domain, which means that we have to use the first equation. So that would equal 1 minus to the power of 2. So that's about 1. So the limit as x approaches 1 from the right, remember that the values of y bigger than 1 to the right of 1 are in this domain, which means we must use this equation. That would be equal to 3. This is the limit of a constant. So number 1 is different than number 3, right? So we're going to say that the limit at x equals 1, or as x approaches 1, for this particular function, k of x, doesn't exist, and the function has a jump discontinuity. So I'm going to say that 1 from the left, limit 1. 1 from the right, limit 3. At 1, limit doesn't exist. K of 1, on the other hand, remember that k equals 1 is in this domain, would be equal to 1 squared. So we're going to say that the function is discontinuous at x equals 1. Now, this is actually something we can skip ahead. And we're going to take a look at infinite discontinuities now. So we have to analyze the continuity of 1 over x at x equals 0. So first we're going to have to find the limit as x approaches 0 from the left, 0 from the right, that's infinity. So at 0, we're going to say that the limit doesn't exist, and that is because left and right hand limits don't agree with each other. So the value at 0 is undefined. So the continuity, so if we were to discuss the continuity, we'll say that the function is discontinuous. And judging by the limits from both and right hand, we're going to say that the function is experiencing an infinite discontinuity because they're going in opposite directions in here, okay? And the gap never stops increasing, right? So the limit at the given point doesn't exist. The function at the given point is undefined. the value of the limit and the function are not relatable, really, in any way. So therefore, the function is discontinuous. Now we're going to take